So this next section, I like this one. It helps us think through our probability. If you can calculate probability, there's no reason that you can't do conditional probability. You've just got to be sure you understand what's being asked. So conditional probability means this. When I'm calculating the conditional probability of something, I am calculating the probability of event E2. All that little 2 means is second event. That was just my notation. So I'm calculating the probability of a second event occurring given, okay, so given that we know, this is the information we know, given that the first event has already happened. That's called the conditional probability. The notation for that is this. We still use the P for probability. We want the probability of the second event, meaning E2. This little bar here is pronounced given that. So when you're reading this, so it's the probability of a second event given that the first event has already happened. That's what that notation is telling you. Okay, so here we go. Example 1. I'm taking a single deck, or excuse me, a single card from the deck of cards. What's the probability? It's a club given that it's black. Okay, so what's the probability that it is a club given that it is a black card? I'm going to give you a second to write that down. Then I'm going to tell you all you need to know for this class to calculate conditional probability. Remember, probability in general is my successes divided by my total number of outcomes, right? Successes divided by total. So when you're doing conditional probability, what happens is now we're not considering the whole deck of cards anymore, right? We know some information. What do we know about the card that I'm holding? It's black. So this right here, whatever this given information, this becomes your new total. Okay, that's how you think about this. The given information is the new total that you're dealing with. So how many black cards are there in the deck of cards? There's 26. So that's my denominator now. That's my new total. Now, out of those 26 black cards, so I'm not thinking about anything else. I'm only thinking about those 26 cards now. Out of those 26 cards, how many of them are clubs? 13. Okay, so 13 divided by 26, I put that in the calculator, that's 50/50. Okay, well, I would like you to go ahead and do the same sort of thing. Example 2, conditional probability. What's the probability that when you draw your card, it's an ace, given that you know it's a number card? Okay, so again, whatever the given information is my new total number of objects. So in my deck of 52 cards, how many of them are number cards? What are you considering number cards? Okay, yeah, that would be the normal thought process, and I totally understand it. So if you did it that way, but when I talked about the deck, I said we are going to consider the ace to be 1. Okay, so we're doing that. I know that's not necessarily natural if you're used to playing cards, but that's what we're going to do. So in that case, then we're going to have 40 number cards. Okay, so I got 40 number cards, and out of those 40 cards, how many of them are aces? Yep, there's 4 aces in the deck. So that is 4 out of 40, or you can reduce it to 1 out of 10 or 0.1. So you got a 10% chance of picking an ace if you know that you've got a number card. So this is conditional probability is kind of the basis for a classic statistics statistics problem. If you take statistics, you might talk about this called the Monty Hall problem. You probably have no idea who Monty Hall is, which have you ever heard of the game show Let's Make a Deal? they've revisited it with the guy from Whose Line Is It Anyway, and he's from Orlando. I forget his name. Anyway, all that to say is the premise of it is this. Before you have the 3 doors and you pick door number 2, right? And then they reveal what door number 2 is, and it's the sheep or whatever. And so then they say, okay, do you want, or no, maybe they don't reveal, whatever. And so then so Monty Hall says, do you want to change your choice? And so then the question statistically is, should you change your choice? If you've picked your window and you don't know what's in it, but he asks you, do you want to change? Is it to your advantage to pick a new window? That's all based on conditional probability. So if you ever encounter the Monty Hall problem, think of me while you're talking about it, because it becomes a lot of fun. All right, whether or not you care about that. Example 3. Example 3, I've given you these 6 circles. They have different colors and different numbers. And I ask you to do 3 things. Now, the first thing is just a straight probability problem, just to remind you of the difference. And then there's 2 conditional probabilities. So give it a try. Wayne Brady. That's his name. I'm terrible with names, but I got it.
Are the green for orange too?
That doesn't matter. Don't worry about the color of the actual numbers. The orange refers to the color inside the circle. All right, so the first one says, what's the probability that I pick a 5? Now, there's no condition there. So since there's no condition on this one, what's my total number of outcomes on this one? 6. Yes, we consider all 6. And out of all 6 of them, how many of them are 5s? 1. I'm going to leave that as a reduced fraction. You can make it a decimal. That is your prerogative. Okay, the next one's a conditional probability. What's the probability of it? It's a 5 given that it's orange. Okay, well, how many orange circles do I have? Okay, I'm going to underline them. I've just got these 3 right here. That's my new total number of outcomes. Out of those 3, okay, I'm only considering those ones. Out of those 3, how many of them have a 5? Okay, so my probability changes when I know that I have an orange circle. Okay, what's the probability it's even given it's not orange? So the ones that I haven't underlined are not orange. So there's also 3 of those. And given those, what's the probability I have an even? How many evens are there? 2. Okay, again, I'm only considering the evens, so don't worry about this 4. I know it's even, but remember that 4 is not part of my given information. That 4 is in an orange circle. It's not in a circle that is not orange. We doing okay with conditional probability? Okay, well then give the next one a try. It's just conditional probability from a table. Okay, again, the first one is a regular probability, and then the other ones are conditions. Give it your best shot. See how you do. All right, so the first one is the probability is somebody is satisfied. Again, that's not a conditional probability. So what is my total that I'm going to work with on that problem right there? There's 250 people in this survey, yes. And out of those 250, how many of them are satisfied? 210. Is everyone tracking where these numbers are coming from? Okay, that's my big purpose in this, is that can you read the table? So 210 divided by 250, that reduces to 21 over 25 if you want, or you can make it 0.84. So far, are we so good? We doing okay? Okay, now this is where it gets interesting. Make sure you can read the table. The next one says, what's the probability they're satisfied? But now I have some given information. They've had knee surgery. So what's my new total number of outcomes I'm going to work with? How many people have had knee surgery? Okay, so my total, I only care about this row right here. So how many people have had knee surgery? That is 95, not the 75, but the 75 is going to be part of this. So out of those 95 on this row, I only care about this row now. How many of those knee surgery people are satisfied? Does everyone see that? It's a common mistake. Okay, that's why I'm going to have another table for us to go through just to make sure we iron out any of these issues while we're together. And that is going to be 0.7895. So if you missed that, that's okay. Remember, we're here to learn. And so we're going to get more opportunities. The next one is, what's the probability of heart surgery given they're dissatisfied? How many dissatisfied people do we have in the table? Okay, there are 40 dissatisfied people. I am going to circle the dissatisfied column. Now I only care about that green column. I don't care about anything else. Out of this green column, out of those 40 people, how many of them had heart surgery? Okay, 5. Everybody tracking where these numbers are coming from. Please speak if you are having trouble. Okay, that is 0.125. Then last but not least, what's the probability they're dissatisfied given they've had heart surgery? So what's my total number of outcomes going to be this time? 50, just the heart surgery people. I'm going to circle this one in black. Okay, so just these 50, just this row is all I care about on this problem. And out of those 50, how many of them were dissatisfied? 5. So that 5 out of 50 is 110 or 0.1, 10% chance. All right, last but not least, we are going to finish this section. We've got plenty of time. So you've got 5 problems left. I'm going to give you 2 minutes. Again, I just want to make sure we can read these tables because that's sometimes a point of confusion. All right, just for time's sake, if you got any questions, let me know. So the probability of a good bulb, there's no condition. So my total number of objects are 330. And out of those 330, how many of them are good? 300 of them. Great. I'm going to make a decimal out of that. I'm going to take my 300 divided by my 330, and that is 0.9091. Okay, now we get into the conditional probabilities. The next one is the probability it's good again, but now this time I want to know, okay, does it matter if I know I have a 100-watt bulb? So basically, if this is an example of something that's looking sort of real world. If you were a quality inspector, you would do this. You would want to know, does the quality rate vary depending on the type of bulb? So 100-watt bulbs, I've got how many 100-watt bulbs in this one? 130. Out of those 130 100-watt bulbs, how many of them are good? 120. Okay, so that's 12 divided by 13, and that is 0.9231. So you can see, according to this data, that my 100-watt bulbs, they perform better as far as the manufacturing process seems to go. Okay, the next one says, okay, well, what's the probability that it's 100 watts if I know it's a good bulb? So I'm reversing the condition. So this time, how many good bulbs do I have? 300. You already answered that for me, but appreciate you doing it again. Out of those 300, so out of this column, how many of them are 100 watts? So 120 divided by 300 turns out to be 0.4. So 40% of the good bulbs are 100-watt bulbs. What's the probability it's defective, given that it is a 20-watt bulb? So how many 20-watt bulbs do I have? Okay, yep, 95. That's just this top row right here. And out of those 95 20-watt bulbs, how many of them are defective? Yep, it sounds like you're reading the table good. So I'm glad for that. If that is not true, please make sure to speak to me and let's get anything out in the open. And the last but not least, what's the probability it's greater, or excuse me, good, given that it's greater than 20 watts? So how many bulbs greater than 20 watts do I have? Yeah, so we're talking about these two rows this time, the 50 watts and the 100-watt bulbs. Those are the ones that are greater. And out of that, you said we have 235, and that was exactly right. And out of those 235, how many of them are good? 220. So 220 divided by 235, that is 0.9362. And there we go. That is conditional probability. Just make sure that condition is your new total